Sorry for interrupting. I wanted to ask, this project is like a midterm project? We will have a midterm or not?
No, we are not going to have a midterm, a written midterm. It will be a project based. Okay.
It's only for the midterm or?
The first, now these projects, they're going to have a deadline, and when you submit this at the specified deadline, that will be the grade for the midterm. Now, if the project has, let's say, I know how much you can submit in 2 or 3 weeks, but then if the project is, it can be expanded further. For some of you, whatever you submit in the midterm phase, you can submit it also at the final phase for the final exam as a final project. So what I want to say is that for some of you, the same project will be for the midterm and for the final, but the grade at the midterm stage in time, which would be in a few weeks, that one will account for the
midterm.
Okay.
But for final, we will have a final exam, or also it can be used as a final project. We can work again.
The final will also be a project based, and as I said, for some of the projects that you are going to submit, there is enough. There is a lot of work to be done, which might include also, as much as you can improve, it will still count for your final, because you might not finish them until the midterm. In a few weeks, you might not cover a lot of work. So that's what I mean with this. Okay.
Okay. Thank you very much for your explanation, Professor.
You're welcome. You're welcome. Okay. So from the last time, we were discussing about the singular value decomposition. Let me see the board. Okay. So let's say that often, if we have any matrix which is of the form, so if it is a matrix which is a square one, we said that we can diagonalize them. So we can get a matrix which is n by n, a diagonalized one, using the eigenvectors. Okay? Using eigenvectors, and when the matrix is not a diagonalized one, we cannot use the eigenvectors because the eigenvectors is defined only for square ones. We can use the singular value decomposition. Now, regarding the importance of this important concept, so let's say we can simply generalize this as such. We can have a square matrix which is n by n, and another square matrix which is n by n, and still we want to get, let's say, now this D, P, and here we want to get the A, which is equal to U sigma V transpose. So now these two approaches, so this is using the singular value decomposition, and these both, we call these the diagonalization. So this is, and this is very important because the diagonalization, in essence, what it is doing, it is projecting most of the weight of a specific problem or of a specific solution onto orthogonal coordinate system, removing the coupling. So we have no coupling, and removing the coupling, it is defined as the having no projection of one variable onto the other. Now, one example that we can provide is, for example, the following. We can assume we have 5x squared minus 6xy plus y squared. This is equal to 2. So let's have a look at this problem. In principle, this is just an identity, or it's a statement that that reports a relationship between x and y. Now, but we know that for each x, we can get a y, and let's assume, for example, so this can become as simple as this. So if you set x is equal to 0, what is y? Y is equal to square root of 2. Okay. If we set y is equal to 0, this is simple for us. We can figure out that the x is equal to square root of 2 over square root of 5. Right? So x would be equal to plus minus square root of 2 over square root of 5. And we want to get an understanding of how, of what this identity is telling to us. Now, we see that Now, what is the relationship of this expression with matrices? Let's see if we can construct one relationship. But let me ask you this: what is the size of this 2? If this 2 is a matrix, what is the dimension of this matrix?
One by one.
That's true, it's 1 by 1. Okay, so any scalar is a matrix which is 1 by 1. And here we have also an expression. But what is very important in many advanced mathematics courses or advanced engineering problems is that we can try to write this expression to express this in a matrix notation. Okay? Why do we care about matrix notation? Is that it is very useful, and sometimes it can even help us to reduce the dimension, to reduce the complexity when we calculate something. And also, it can provide for us some new representation to even make this look a little better. Now, the way to write this, it would be the following. Often, you might see this approach that we want to write X transpose times a matrix, which could be a square matrix, times another vector X. This is equal to, let's write it equal to 2. Okay. So now, how can one reformulate that statement into a different form? Now, imagine for a moment that this vector x, this is the vector xy. Okay, so it's this one. So one possible approach is that this is x, and the transpose of this one is going to be as such. We have here x and y multiplied by 5 minus 3 minus 3 5 multiplied by x y. This is equal to 2. So this is one way to write this one. If we have any doubt, first of all, the dimensions. Here we have 1 by 2. This is 2 by 2. This is 2 by 1. And if we multiply two matrices, which are 2 by 2 and 2 by 1, we get 2 by 1. If we multiply 1 by 2 by 2 by 1, we get 1 by 1. So this is what we can get. We can check this one, whether this is true. So if we multiply this row with this column, we get 5x minus 3y minus 3x plus 5y. Here we have a vector. We multiply here with xy. I'm sure that most of you might see this one. This will be equal to x times the first term. We get 5x squared minus 3xy minus 3xy, which is coming from multiplying the second term with this one, plus 5y squared. This is equal to 2. So that's good. We wrote this equation here, and now we want to represent this in a simpler way. How can we do it? Whenever we talk about the diagonalization, we are talking about a schema which involves a domain which is defined by a basis, and here we have a standard basis. Okay, so this is the standard basis, and standard basis it includes 1, 0, 0, 1, right? So this is what the standard basis is, which would be the Cartesian coordinate system, which is going to look something like this. So here we have 1 and 1. Now, in this basis, we have the vectors, actually more essentially, we need to put here this 5, minus 3, and 5. Okay. So we see that now this looks like it is an identity which expresses polynomials of the second order. Then this is the matrix. We can think that, let's try to simplify this one. How can we simplify this? From a matrix A, we can obtain here a matrix B, which is diagonalized. So we can try to do this, right? And then let's try.
Pensa de duas niches, nós está para nevar na dig na cifra.
Sorry, can you?
The matrix should be 5 minus 3 minus 3, 1. Not 5 again. That's the matrix.
Okay, let me see. So you are saying this should be 5 minus 3 minus 3?
1.
1?
To match with the upper.
Yes, you are right. Okay, again, you're right, but for then what if I write here a 5? Maybe I make a mistake here.
Yeah, it's good.
Okay, that's a good observation, Gendy. Thanks for that. And now the question is that we have to find a way how to represent this better. Which one is that? This is a square matrix. Let's use the eigenvectors. What are the eigenvectors? We have to identify. We have the matrix A minus lambda I. This times x. This would be equal to 0. So why do we use this notation? Because we know that because we have the eigenvalue equation which states that Ax is equal to lambda x, right? So we have to consider vectors which the matrix does not rotate at all. Okay, so this is the one way to think about the eigenvectors. They are not rotated by the matrix. Then from here we get this expression, and finally we get here the matrix 5 minus lambda minus 3 minus 3 5 minus lambda. Now this is, and we know that this expression, this is equivalent to writing like B, matrix B, times x, this is equal to 0. Solving for x, this is equivalent to finding the null space of this matrix. Null space is composed of the union of all vectors of x that satisfy this condition. Okay? And then the first solution here is a trivial solution where the x can be equal to 0, but we are not interested into the trivial solution. We'd like a more general one, and x can be different from 0. X as a vector can be different from 0 vector if the determinant of this matrix B, or A minus lambda I, because B, we're just writing this one as A minus lambda I, only if the determinant of A minus lambda I is equal to 0. And we know that from this expression, we get the characteristic polynomial, which is going to be a second order polynomial. And here, this would be equal to 0, the determinant. This is going to be 5 minus lambda. 5 minus lambda squared minus 9, this is equal to 0. So we expect two different solutions for lambda. And from here, we obtain lambda squared minus 10 lambda plus 25 minus 9 plus 25 minus 9, this is equal to 0. So then we get lambda squared minus 10 lambda plus 16, this is 0. So it looks like we can find a couple of lambdas where the first one is 2. So lambda 1 is equal to 2. And if lambda 1 is equal to 2, we have to find the respective eigenvector. What is x1, which stands for lambda 1 equal to 2? We have a vector which satisfies this condition. So we have here 5 minus 3 minus 3, 5 times the vector AB. This is equal to 2AB. And this 2AB, we have to extract the equation from here. We get 5A minus 3B is equal to 2A. So we have two unknowns in order to find an eigenvector. If we have two unknowns, how many equations do we need?
Two equations.
We need two equations, right? Can we get a second equation here? We need two equations, but the first one, we got it by multiplying the first row here with the column here. Can we get a second equation?
Yeah, minus 3a plus 5b is 2.
Sorry, is it 8, the second?
Say it again.
8 or minus 8, one of these.
You mean the lambdas?
Yes, lambda.
Yes, one of the lambdas it is 8, but the other one is equal to 2. Okay? So, for example, Johan, this expression, this can be written as lambda minus 8 times lambda minus 2. Okay? So this one, this is lambda minus 2 times lambda minus 8 is equal to 0. So you are right, we get one of the values is this, okay? But my question is here. In fact, I just want to remind you that if we have two unknowns, we need two equations. The first equation is this, the second equation is this. Do you agree that we have two equations?
Yeah.
In fact, we don't, because the second equation, it is linearly dependent with the first one. Because from the first one, we observe that we have 5a, this is the first one is 3a is equal to 3b, right? If we take this 2a to this side and 3b to the other side, we get this. From the second equation, we get, again, we get 3a is equal to 3b. So in principle, we don't have two equations, we have only one, and we know this because we are considering a case when the determinant of this matrix B is 0. So it's true, we can construct two equations, but they are both linearly dependent, so in principle we have only one, and it looks like one of the eigenvectors, it is when A is equal to 1, 1. So the eigenvector is, wait a second, so let's do it like here, x1, which corresponds to lambda 1 equal to 2. We should do this faster because we all remember this, but so this is equal to 1, 1. Now that we found, this is the first eigenvector. If this is the first eigenvector, this can serve as a basis for the new domain, okay, for the new domain. Then let's find the other lambda, the other eigenvector. So this is all regarding one of them. Then for lambda equal to 8, we have this expression. So let's do this here. This is equal to 5 minus 3 minus 3, 5 times AB. This is equal to 8 AB. And we know that we have a single equation. Here we have 5A minus 3B. This is equal to 8A. So from this expression, we get that 3B minus 3A. This is equal to 3B. So from here, we get that A and B are negative with respect to each other. So the second eigenvector, it is minus 1, 1. Okay? So we were given a polynomial, then we obtain this, and it looks like these new eigenvectors, the eigenvectors of this matrix, they define this vector, which is 1, 1, and this is minus 1, 1. Now, they both serve as a basis for R squared, because we know that for two-dimensional space, we need two vectors that are linearly independent. For seven-dimensional space, we need seven vectors that are linearly independent. And these, for 30-dimensional space, 30 vectors that are linearly independent, and so on. So we are good. This is really a basis, but we can call this one basis B. And this is a standard basis, because this is defined like this. Now, what is the use of these two vectors? These two vectors that we see here, which are the new basis, they can be used to transform any vector from the, no, this is the other way around. So from any basis, we can go to the standard basis by applying a matrix. What is the notation we have used so far? Let's call this one matrix P. Okay, so any vector in this domain, we can find it in this domain in the standard basis, and here we can move backwards with P inverse. Now, so given these, we can then say that in the new, if we do the change of the, well, let's ask it this way. What is the difference between this basis and the other one? The original basis, the standard basis, here we have a 90-degree angle, and in the new basis, we also have a 90-degree angle. So it looks like we have rotated the coordinate system by an angle of pi over 4, right? So we have rotated it by 45 degrees, and this is what we get. Now, a rotation by 45 degrees, what is it? Oh, sorry. So this was 5x squared minus 6xy, and this is equal to this. Now, in standard basis, we have here xy, and in the other basis, we can consider a capital X, capital Y. And then, what was the linear transformation that we can move from one to the other? Is the matrix, is the rotational matrix. So, if this is the rotation by pi over 4, rotational matrices, they can be written as such. So here we have cosine pi over 4 minus sine pi over 4, sine pi over 4, and cosine pi over 4. And if we substitute the values, what we get here, we get 1 over square root of 2, 1 minus 1, 1, 1. Okay. So this is the linear transformation which relates one pair of vectors in one domain with another pair of vectors in another domain. So from this expression here, let's see again. Wait a second. So yeah. So if this is the case, then we say that the x and y in the standard basis SB is equal to 1 over the square root of 2, 1 minus 1, 1, 1, times x, y. Okay. So if we have a look at this one, we just need to, we see that the little x here, we are going to write the following. We have 5 times 5x squared. And I can write this here. So little x is equal to 1 over square root of 2 from here. X minus y. And little y is equal to 1 over square root of 2 x plus y. So with this change of variables, we move ahead. We say that 5x squared. What is 5x squared? 5 times 1 over 2 times x squared minus 2xy plus y squared minus 6xy. Minus 6xy. Now, if we multiply x and y, we have here 1 over square root of 2, 1 over square root of 2, we get here 1 over 2. And x and y, if we multiply these, we'll get x squared minus y squared. And then we have again plus 5, we have the y squared term. Y squared term is here. So this is times 1 over 2. X squared plus 2y squared plus 2xy plus y squared. This is all equal to 2. And then we look at these solutions. We see that we have here x squared is 1 here. This is another x squared, which makes 5 over 2 plus 5 over 2. This is 5. And then we have here minus 3. We get 2x squared. This is 2x squared. Then we look at the minus 2xy. This term, it cancels this term because it is 5 over 2 times 2. This is minus x. So this is minus 5xy plus 5xy. Simply, just by looking at the expression over there, we do cancel out. And then we look at the final values. This y squared, this is 502 epsilon 4, 502 epsilon 4 ed el pes, 5 epsilon 4, plus 3 ed el p. to tail. Epsilon Cator, this is all equal to 2. Okay? So this is this polynomial which is using in the standard basis. And the standard basis, we consider the basis which is the Cartesian coordinate system, which has here x and y. Now, when we move to a new basis, which is here the capital X and the capital Y, and how do we do this one? How can we go from the X in black to the XY in red? By using this rotational matrix. And this rotational matrix, we can use it to go, as I said before, from this domain to this other one, which means that to effect, we can rotate this vector with this matrix, and we should get this. And then it looks like if we are trying to write the same equation using this notation, how can we do it? This notation, we can denote this one as capital X, capital Y, times the matrix, which is 2, 0, 0, 8, times the vectors X and Y. And this is equal to 2. Now, if we look at this expression here, and we compare with this expression here, we can really see that we are able, apparently, we are able to diagonalize this system, which means that we zero out the off-diagonal terms. So often, even when we use the singular value decomposition, our objective is to represent the whole data set in a new domain where off-diagonal terms, they are equal to 0. Now, let's have a look again. This means that we can obtain this representative matrix, which is going to be the diagonal matrix. In fact, it is clear what the diagonal matrix is going to be, because we can simply include the eigenvalues in here, like 2, 0, 0, 8. And then what we can do is that immediately we can write them like this, and we are pretty sure that it's going to be the correct solution. But we also, how can I say, we also did it the other way around. We derived these values just by assuming that in the new basis has been shifted by an angle of pi over 4. So, based on this argument, we rewrote the rotational matrix here. Then we define what x and y can be, which is seen here. Then we wrote the small x and y as it is expressed here. We substituted. This is what we got. So this is one way of how to remind ourselves of how the diagonalization can work. Okay? This is what it does. And again, we can also remind each other that the diagonal matrices, or let me say it this way. Okay. Now, these matrices that we see that we can move from one side to another, they are simply used if you want to transform only a vector. But if we want to transform a linear transformation, and a linear transformation, let's erase some part from here. So probably, okay, so let's take out this part. Okay. So here we can say we have some linear transformations that can look like this xy. Linear transformation, as just a small reminder, is that it can be x plus y, x minus y, 2x plus 3y. Okay. Now this is a linear transformation which can be simply represented by a matrix, which is because T on x, this is going to be equal to AX, where A is a matrix. But T is not a matrix, it's a statement. This is a statement. And what is A in this case? A in this case is equal to 1, 1, 1 minus 1, 1, 1, 1 minus 1, and 2, 3. Now, this is a linear transformation, and this is the representative matrix. Now, these linear transformations, what we see here, this is the transformation on the standard basis. Often, what we need to do is that, I believe you cannot see all of it, but let's assume that this is a basis B, and here we have another basis S. Another basis B and S. And often, we might be given a linear transformation in the standard basis, okay? But we want to see how a linear transformation in B looks like, how a linear transformation according to this basis, how it looks if we're talking about this other basis. And now, this is when we're switching from one basis to another. And what you might take for granted, which we're not going to prove it here, is that, not to prove, but to remind, if we don't go too deep into the linear algebra principles, we can report that the relationship between the standard basis and any one of the bases, it can be represented as such. So, P of x, of any vector x, or wait a second, let me do it like this. A represents linear transformation T in standard basis, in SB. Okay? And then we have the P inverse times A times P represents the linear transformation in a new basis, B basis. So this is a different one. If you consider our example here, we are just talking that we might have this basis versus this. So summarized, maybe I can say this one in short, like this. Any linear transformation represented by a matrix P in standard basis is this, but if you go to a different basis, we use this P inverse A times P. Which means that this transformation, let's see what we get. And by the way, this is a definition which some of you might remember, some might not. Is that if this is a different matrix C, these matrices, if we can write a relationship as matrix C is equal to P inverse A times P, we call this similar matrices. So it's a similar matrices. Now, in fact, we can use this. I don't need to show it over there because you can all try Octave Online or MATLAB. Okay, I think I have this one. Of course, I do have it. Okay, share entire screen. So, wait a second. Yeah, let's have the matrix A. This is going to be equal to 5 minus 3. 5 minus 3 minus 3, 5 is the matrix A. Then we can write down a matrix P, which is equal to 1 minus 1, 1 minus 1, 1, 1. So this is the matrix P. And then if we multiply the inverse of the matrix P, multiplied with the matrix A, again with P, this is what we obtain. Okay, so we get this 2008. I cannot even see this correctly. So we really get the diagonal matrix B. So, and for this one, let me use this part here. So apparently, this D is equal to P inverse A times P. And this is the diagonal matrix, which is storing the eigenvalues in the diagonal terms. Now, this is expected from us. We know that always, and again, these are similar matrices. But this does not have to be a diagonal matrix. For any matrix which is assumed that P it's not diagonal, but it's P inverse A. P, they are still considered similar, so maybe I have to write this down. These are called similar matrices, and they have specific properties in linear algebra. But what we care for now is just we care more about the diagonal matrices as we have reported on the board. Now, this was a review, or at least one way how we can transform these identities, which can be written in this form. And this one, even in our textbook, you don't see directly this expression. You don't see this one directly, but you observe this one in. Wait a second. I don't need to share the screen anymore, but it's hidden. Let's stop sharing. Okay. So this was the eigenvalues. The new thing that we can add on top of this is that if we don't have a matrix which is squared like this, but it is 3 by 2, we need to extract the singular value decomposition. But to obtain this, the procedure, it is often that we need to calculate the. Wait a second. Let's take this away. We stayed here long enough. So we randomly generated this matrix. This is 3 rows and 2 columns. And in order to obtain the singular value decomposition, we can calculate A transpose times A. So this is A transpose, it is 2 by 3, times A, which is 3 by 2. We get a matrix B, which is 2 by 2. And similarly, we can also multiply A times A transpose, which is 3 by 2, times 2 by 3. This is a matrix C, which is going to be 3 by 3. Now, after obtaining these matrices, we can find, now these are squares, right? From here, we can find the eigenvalues, these gammas. And these eigenvalues that we see here, they are equal to the singular value decomposition squared. Okay? So these gammas, which we have seen this a little more often than the SVDs, from here we can get these sigmas. Sigmas, or these are the singular values. And wait a second. So if we look at these, this bit is P times A times P. Let me think for a moment. In fact, let's think. So if the diagonal matrix was equal to this, the matrix A itself, which is this will be equal. So if we multiply both sides by P, this is P inverse. We can easily distinguish this because we can multiply it on this side by P, right? On this side by P, here P inverse, here P inverse. This is what we get. This gives identity, this is identity, so we get this. So in fact, in diagonalization, using eigenvalues and eigenvectors, this matrix is represented by a rotation with respect to the standard basis. Okay. Well, let me think for a moment. Yeah. This is like rotation, and also changing some parameters by some values. Now, this is eigenvectors. In the SVD, this one, I'll draw this again on the board. This would be written as a matrix sigma, and another matrix V transpose. And one thing that I can add here, which is relevant to what we are going to see in SVD, and we are saying this one only so that we can easily pick up some properties or remind ourselves. So even before a while, here we have this cosine pi over 4 and sine pi over 4, and this was the rotational matrix, right? And this is the rotational matrix, and this rotational matrix, it has very useful properties because let's try this one. This was 1 minus 1, right? Rotational matrix is rho r, the transpose of any purely rotational matrix. They are equal to R inverse. Okay? And the reason that I reminded here, we know that if this is a rotation of pi over 4, then the inverse of this rotation by pi over 4 is equivalent or is equal to a rotation by an angle of minus pi over 4. So we can rotate by 45 according to some direction. To undo this operation, we just rotate the pi over 4 back. So this one, if we insert minus here, minus, minus, and minus, the cosines, they are not going to change sign, but this would be a minus, this would be a plus. So in principle, the rotational matrix inverse will be equal to the rotational matrix transpose. So this would be the, which in fact, wait a second. Is this wrong?
Ni minus ni, ni.
This is wrong. This minus 1 is here, right? Because sine, this is a minus sign, so now this is correct, right? And actually, it was my mistake, but from here, if we bring these columns down here, this is minus 1, okay? And here, the inverse rotation, here it is going to be, this will become minus, this pen is that. Or maybe it's best if we rewrite this one from scratch. Cosine pi over 4, if you make it minus, it will still be plus. So, because cosine theta is equal to cosine minus theta, so this is cosine pi over 4, this is minus sine, this is sine, and cosine. So we can see that the only thing that helps, we just calculate the transpose. So this is useful because we are going to see, we see also a lot in our textbook, in this chapter, that if we multiply any one of these rotational matrices with the transpose, we get the identity matrix. Now, I try to keep on the board the most relevant informations. Now let's take this away. So, the use of eigenvalues, eigenvectors, or singular value decomposition, what they can help us to do is to identify the correct rotation so that we can simplify our problem. Okay? So we can reduce the dimension, we can do a dimensionality reduction, and the dimensionality reduction, it can be achieved in case we observe that any of the orthogonal orientations or orthogonal directions is 0. So, or the variance in any one of these directions is equal to 0. And now,
Professor,
yes,
can we say that eigenvalues and eigenvectors define the perfect rotation, so as we have the least weight for the graph?
again, you said that, can you say that eigenvalues and eigenvectors are the perfect what?
Yeah, they help us to find the perfect rotation that we need, the perfect angle that we need to have the least weighted graph. So to have a graph.
Yes. Yes, exactly. Because they using those. So, for example, we found eigenvectors here, and we ended up that if we multiply the inverse of this with this matrix and with this matrix again, we found the diagonal matrix. That's true. So that is their task. Okay.
But maybe we do not always take. Do we always take the diagonal matrix when we find the eigenvalues? No.
Well, our objective is to diagonalize the system. Okay, so if we want to diagonalize, we better use the find eigenvalues and eigenvectors, and then those eigenvectors we consider them as a new basis. Okay, because we have two-dimensional space, we come up with two eigenvectors, so this is the basis for R squared. If we have in three-dimensional space, if we have a data set that we want to diagonalize, we are going to have three eigenvectors for a 3x3 matrix, and we hope that they should span the what's the name? The three-dimensional space. I don't know. Am I clear, Gandhi, or?
Yeah, I understand.
Okay. So yeah. Now, so this is what we expressed for this matrices here on the board. And what we can say now is that with all of this discussion regarding okay. Now the theory, we can start this one in so in SVD, A will be equal to a purely rotational matrix times some sigma values times the V transpose. Okay. And this is rotation operation. This is again another rotation by a specific angle. And this is the, let's call this one length changing operator. So if we want to change the length, because if we multiply, this is diagonal, and this is diagonal, and what they do is that they simply multiply specific directions by certain value. So they can stretch or compress one certain values. And let's see, for example, what if you have this matrix 2, 0, 0, 8, if we multiply this one with the vector 1, 2, what we get here, we get 2, and the other value is 16, right? So what did these values do? They simply multiplied each component along the x-axis by 2, and they multiplied this one by 8. Okay? So this is what we are doing. So, and one thing that we have to be aware of, or that we should never forget, is that this A, maybe we should write these. This A, it has dimension m by n. Okay, m rows and n columns, and this is equal to U, and this rotational matrix U. This includes. This is also m by n, and here the sigma, it is n by n, and the V transpose, this is also n by n. And what they assumed that this was a rotation, what this is really doing, imagine for a moment that we have an ellipse. Imagine that we had an example before where we said that we looked at an, wait a second. Actually, no, we did not see that. We did not draw the graph, in fact. But if you remember, we do something like this. 2x squared plus 8y squared. This was equal to 2, right? So this was, what we did not do is that we did not draw the graph of this one. And we said that we even drew this one in color. And I'm doing this drawing just to remind you of something. So this is the capital X. This is the capital Y here. And let's see what is the graph of this representation. So if we put here capital X equal to 0, what is Y? We get 8y squared, this is equal to 2, which means that y squared is 1 over 4. So what is y? It's 1 over 2 and minus 1 over 2, right? Then, if we set capital Y equal to 0, I forgot to do this one before. If we set Y is equal to 0, we get 2x squared is equal to 2. 2 capital X squared, this is equal to 2. So X is 1 minus 1. So it's here and here. So imagine that we obtain an ellipse. Now, if we had here the variables in black, X and Y, which was this equation which had some coupling term. What was the coupling term between the X and Y? It was minus 6xy, right? So we had this expression. In the general initial equation, this was 5x squared plus 5y squared. This is equal to 2. If you want to draw this, this is what we're going to get. But it's a little difficult for us to notice that the graph of this equation here is going to look like this graph in red. Why? Because it's using a graphing machine, and for regarding this, I would strongly suggest for any one of you that does not know there is this Desmos. You can download this on your cell phones, and you can plot any equation you want. It will plot it right away. So if you need to solve systems of equations using graphical techniques, this is really a good software. Okay, so just have a look at this one. And then let's assume that in this new data set, we have this ellipse. Okay? So this is how we look at this data. Now let's assume that we have this ellipse, which looks like at an angle of 45 degrees. Okay? This is a data set. What this rotational matrix can do on this let's call this one. So these are the major axes. On this one, let's apply the V. Now I don't know whether I should go to the left or to the right, because we apply a V transpose on this data set, because it's like the functions. You apply to the left side to see what this is. So now I just drew this one to remind ourselves actually why we did all of that work. So imagine that if we apply a VT here, a rotational matrix, we are going to rotate this one, let's assume a little more, and we make this one almost perpendicular. So the major axes, they are here. And then, actually, I think it's best if I do it this way. So we apply from here to here, we go using this linear operator, this rotational matrix. And then we multiply this data set with the sigma. But what the sigma is, as a reminder, is going to be something like this, which is going to multiply the major axis with constant values. Okay? So let's assume that this sigma is having the values of 2 and 8. So if it has the values of 2 and 8, let's assume that this 2 is around here. So we preserve the angle is the same. This is the center. We have, this is one unit vector, so the length of this vector we project it here. Then we multiply this vector by 2, we get this, okay, starting from here. Then this other component, we multiply this one by 8, which is going to be 1, 2, 3, 4, 5, 6, 7, 8. So now we just join this. Probably this would even be close to a circle, at least depending on how we are drawing it. But this is what happens. So we multiply this by 2, and we multiply this by 8. And then it's best if we preserve. Then we rotate this again, and rotation again. So let's try to assume that this is to scale, and this is like an ellipse. Let's preserve the ellipse shape. This later, it will preserve the length of the major axis, and it is going to rotate it like this. Okay. So this is the singular value decomposition. This is what it's doing. So again, multiplying a data set or having a linear transformation represented by a matrix A, which does not have to be a square one, it is equivalent to getting the data set, rotating it by some angle. So in this case, we have just rotated this one to some degree, counterclockwise. We get this. The sigma is going to multiply the major axis. So this is how we modify it. And then another rotation matrix, this is the U. Then we get this. So this is the effect, or this is what the SVD is doing, or this is how we can represent, so we can also call this rotation, length operation, rotation transpose, which is still rotation. Reminder is that U transpose is equal to U inverse, and similarly, E transpose is equal to E inverse. This is what the unitary matrices do. Okay. Now, so if we have here B transpose, the A transpose itself is going to be U sigma B transpose, and this will be equal to V sigma U transpose. Okay. So then what we can see from here is that if we multiply A transpose with A, this will be equal to B sigma U transpose U sigma B transpose, and this will be equal to, so here we can directly multiply these two by removing these, and since the U transpose times U is the identity matrix, we can simply, or we can see that A, this is equal to B sigma squared times B transpose. Okay. And again, what this looks like, since these are inverses of each other, this is equivalent to saying what we had before. So let's have a look at this expression. We said that a certain matrix, it was equal to, where did we write the A? We wrote the A as B times inverse, which in principle, this is B times the D, because it's diagonal, and let this be, let's write this one as an inverse, because it looks better to the eye when we compare it with this. So apparently, if we multiply a matrix A with its transpose like this, we obtain a new matrix C. I don't know how to call this one, a new matrix C. And what happens is that, so this diagonal matrix, this is composed only of the eigenvalues, because we see that the diagonal matrix, it has the lambdas right here. So assume for a moment that these are lambda, or let's consider this is only one lambda. And here, this is having the sigma squares. Okay, but they are equal to each other. So this means that if we have here a sigma which is equal to 2, okay, then if we multiply A with B transpose, we are going to get a lambda which is equal to 4. Okay, so this lambda will be 4 if the sigma here initially it was equal to 2. So there is also, we can also notice here a relationship between the what's the name? Between the lambdas and the sigmas. So to some degree, calculating the similar value decomposition, it is equivalent as if we are finding the eigenvalues of a different matrix. One thing that is useful is that A transpose times A, it will always be a square matrix. But one thing which is a little strange, which is still okay, but you might notice this one if you go over the textbook or the examples that will come up very soon. In fact, in the lecture notes that we have submitted in the Google Classroom from last week, you can see some examples where we have tried to diagonalize data sets which were not square. Of course, they were not square, but looking at those examples, so I'm just saying, I can freely say this one because we have had this material probably since last week. What is interesting is that sometimes the A can be a matrix which is 3 by 10. Okay? And this 3 by 10, we want to calculate the SVD. How do we do it? We multiply A transpose with A, and we get the matrix C, which is 10 by 10, right? 10 by 10. Because it's 10 by 3. And if we calculate A times A transpose, which is different from this one, we're going to get a matrix B, which is 3 by 3. Okay? So the thing is that once when we do this, the sigmas will be the same. So actually, the most important, the most essential element that we learn from here are these sigmas. Okay. Another thing that we try to, which is very, very important for us, is when we look at this sigma matrix, how much weight is located at the top values. So these sigmas, they're going, actually, it's best if we give an example, actually. That's what we should do. So these sigmas, they will come up, they will be written in such a form. Here we have sigma 1, it's a diagonal matrix, it's full of zeros. It goes like this, 0. We get here a sigma 2, a sigma 3, and all of these sigmas, they are ordered in the decreasing order, where the largest value will be the very first one, and if the first one, or we can say like this, the energy which is located in the first sigma, this is defined as sigma 1 over the summation of all sigma I, and often, if the problem can be easily diagonalized, we might expect, let's say that, I don't know, I'm just saying some numbers, okay, 70% to 90%. We can have a lot of weight in a system which has a specific pattern, okay? If you remember, what was the example we solved the last week? The last example we were solving, I think we were randomly generating, what was it? Okay, we are randomly generating data points in two-dimensional space. So what I'm going to say right now is very important. So last week we were, I'm trying to remember what we did. Okay, last week we were generating points which were randomly generated in R squared in two-dimensional space. And then we were trying to find the major axis, where the major axis, it is defined as, so in this case, the major axis, it would be this one, the ratio. This one divided by this. And we noticed that the ratio between the two major axes, it was something like from 1 to 3 or 1 to 4. Normally, if this data, it is strange, because they were really randomly generated. So if they were randomly generated, what is the preference of this axis with regard to this axis? Okay, so what makes this having more weight? Then what we tried the last time is that we increased the number of randomly generated points, and then when we were calculating the ratio between the major axes, as we were increasing them, so as a number of data points, which are here, which can be described like this, as this was increasing, then the ratio of axis x1 divided by x2, this was converging to 1. Okay? So this would be because we have more randomness. It is strange that we did not have that much randomness and small number of data points, but this would be possible. Now, a similar this discussion can also be followed here when we calculate the sigmas. Imagine for a moment that we have a matrix which is whatever size it can have, 10 by 7. And we want to observe how random these sigmas are. Okay, so if we have a 4 by 4 matrix, okay, if we have a 4 by 4 matrix and we want to calculate the sigmas, what percentage of the weight would we have in sigma 4? How would you answer this question? Any possible answer? So the problem is like this. If we have a 4 by 4 matrix, we generate the sigmas, and the sigmas, what they correspond to, they correspond to the weight. In fact, it's something like this. It's very close to this idea. So, what can you say, or how would you compare sigma 1 divided by sigma 1 plus sigma 2 plus sigma 3 plus sigma 4, right? So we're finding the weight, relative weight of this first axis. Because in 4-dimensional space, we have 4 different directions, and the weight, or what's a varianza, varianza to standard deviation. We get positive par, not yet catch. So how do you compare this with sigma 4 divided by sigma 1 plus sigma 2 plus sigma 3 plus sigma 4?
Maybe they can change with a factor of 100. I think.
Say it again, get it?
Maybe sigma 4 over the whole sum might be 5% or less.
Okay, so you are Gendi, you are assuming that since these numbers are ordered from the largest to the smallest, you are assuming that it's going to be smaller. But imagine for a moment that you are generating a random matrix. You have a random number generator, and you are generating a matrix which is 4 by 4. If these are random, how would sigma 1 and sigma 4 be related? And the question was, we can also formulate it like this. What percentage of the weight will be on sigma 1 and what percentage of the weight will be on sigma 4? One possible answer, Gendi, is to have them equal. So sigma 1 and sigma 4, they might get equal weight, which means 25% will be on the first coordinate axis, and the projection or the standard deviation or the variance along this axis will be represented by sigma 1. Since the numbers are randomly generated, of course, numerical analysis will produce a number which is somewhat different from sigma 2. Okay? We don't get infinite precision because we are not dealing with integers. But sigma 1 then should be equal to sigma 2 in theory. And sigma 2 should be equal to sigma 3 equal to sigma 4, which means that sigma 1 and sigma 4, they might be 25% here, 25% here. Okay. Assuming that we have a random matrix. We can try this one, right? Yes, sorry?
I was just judging from the energy that you had written on the table, since sigma 1 has almost up to 90% of the energy of the system.
Oh yeah. This was, you know, I talked about this one getting before saying that we have randomly generated number. I just wanted to say with this statement before that since this will be ordered from the largest to the smallest, you might expect in some data sets to be something 70 to 90. But later on, I should have erased this one. I was discussing about the randomness. Okay.
All right.
Okay. So so it looks like if we have randomly generated data set, this is what we should get. Now, what is an interesting exercise would be the following. Would be this. Generate matrix I matrix A. So let's assume, so these are the axes which is showing the variance. Let's assume we are measuring meters, okay? We have some data points which are distributed, or assume the following. You have the cloud. You have the cloud area, and every point of water droplet in the cloud is a coordinate which most probably is random, right? It is out there, maybe the wind is blowing, and it will create a shape like an ellipse. But imagine you have a beautiful round shape cloud, and the location of location of every point is measured in meters, which means that the standard deviation or the variance is square of the standard deviation. You know this, right? So sigma is always equal to the square root of variance of phi. So or they are also related to these sigmas here. Assume that this is not completely random, but I give the example of the cloud of CTRS only to assume like some data points which are distributed somewhere. And let's assume for a moment that they are not equal. We might expect that the sigma 1 is somewhere here, assuming that they are in decreasing order, okay? So this sigma 2 will be here. Then if we have some weight around here, sigma 3 and sigma 4, often you might see them jumping down there, okay? So you might need to zoom in to see them. But let's assume that it's not that extreme. We have sigma 3 here. And a good exercise is the following. What you might do, you might have a for loop which you do the same procedure 21 times. Why do we do it 21 times? Because we might want to draw the Gaussian distribution of a data distribution, and having an odd number is good. Actually, which means that if you want to draw a Gaussian, you need like 1, 2, 3 data points. It's still not enough because you need something like this. 5 data points is best. Okay, so you can draw a Gaussian. That's why I'm just saying 21, which if you have 20 or 18, is such a large number, you don't need to do it. But I want to preserve also the odd number. Now, you can do this 41 times. You can randomly generate matrices which are 3 by 3. Okay. Then you can find all the sigmas. You can find what is sigma 1, what is sigma 2, what is sigma 3. And here you can, which means that you are going to generate how many values for sigma 1? 1, 2, 3, up to 21. So you have an Excel sheet, you have 21 values for sigma 1, and then what one can calculate for sigma 1 would be the following. You can calculate sigma 1 average, okay, plus minus the standard deviation of sigma 1s. Okay, the 21 values, fine, you calculate this. You have 21 values of sigma 2, and we can get also sigma 2 plus minus the error in sigma 2. Sigma 3 would be plus minus the error or the standard deviation in sigma 3. And then the next question could be the following. Show them, okay? And how they could look like, what you can do here is that you can use these values to draw the distribution or the histogram, assuming we have a normal distribution, and the normal distribution would be something that looks like this. Exponential to the power minus x0 squared divided by 2 sigma squared. So you can do this one, you can draw, because this is the normal distribution, this is the Gaussian distribution, and you can do this by assigning x0, this x1, the sigma 1, and this sigma down here is going to be the error that you can obtain from the sigmas. So now, if the data is random, or if the data has some pattern, depending on whether it is it has high randomness, or depending on the possibility of having very low randomness, you might draw or you might expect how much these distributions are going to overlap. Okay? I'm not going to write anything for the moment, but you might expect to have some like Gaussian distribution with I don't know what width, and you can see how much. Well, it depends whether they could overlap or not. Now, in the case of a purely random data sets, which we have 4 sigmas, you can start to think now where sigma 1, sigma 2, sigma 3, sigma 4, where they will be found on the x-axis. And here, on the y-axis, this is the, how can I say this one? This is the frequency. Frequency, this defines or counts how many values of sigma 1 are found. Okay, so there might be this much, and how many frequency here, a little larger value, we get this, and this is the frequency. So for this value, you might find it within this acceptable range, where here we have this magic value of the sigma or of the standard deviation. I apologize because sigma, so let me call this one as the standard deviation. So sigma everywhere, and this might be a little confusing. Okay, then we can have a. Now this was some theoretical aspect of these SVDs. We can have a look at some examples. So, in fact, for any data set, maybe I should have written this on the board, but we always can try to determine a covariance matrix. A covariance matrix shows, in fact, how much overlap is between orthogonal directions. But let's see, let's try to identify, let's look at this example. As you said, actually, these are also in the slides which are shared before, so you can. So here we have a vector x, and this, not vector, it's a matrix x. So apparently we have 3 by 6, and we can compute the mean for each row. And after we compute the mean for each row, so these are apparently, we have 3 rows, so we have 3 different values. So this Mn is equal to 3. Okay, the first row has a mean of 1.33, the second one 2.16 and 1.83. Then we can calculate, we can subtract the mean, because after we subtract the mean, this is equivalent to, so let's say you have a cloud which is up there, and the coordinate system is here on the ground, x, y, z, so the zero of Cartesian coordinate system is down here. But by calculating the mean of all of the position of the water vapor molecules which are in the cloud, by subtracting the mean, what we are in principle doing, we are carrying the Cartesian coordinate system here on Earth directly to the center where the cloud is. Okay, so we are centering the data set, or we're moving the coordinate system right at the center of our data set. So okay, so we have here, we have to generate, we have to update the values of x. Now, here we can calculate the variance of the data set, and sorry, the covariance matrix. And this covariance matrix is equal to x cross x times, wait a second, okay, so we have to, I need this n, and then here we find the covariance matrix, C of x, and this C of x, let's see how this looks like. So since we calculated this one x times x transpose, the size of this will be 3 by 3. We talked about this one, but this one does not look very good because I'm not sure. So it's not diagonal, but what we can try here is let's try to identify the eigenvalues and eigenvectors of this Cx, and this is what we said before. We said that we multiply the matrix with this transpose, then we find the eigenvalues of this, and that is going to tell us important elements. So here, actually, this VD, D is a diagonal matrix. Apparently, the eigenvalues, they are 6, 17, and 21. And if these are the eigenvalues, maybe we can have a look also at the eigenvectors. So here we have 3 eigenvectors, and these eigenvectors, the norm of all of the columns is 1. So the length of these vectors is equal to 1. And here, let's generate here. Okay, so this is the vectors. So now, from here, let's look at this for a moment. We arrange. So lambda. Now lambda was equal. Let's see what this lambda is. Lambda. These are the eigenvalues that we found, but now they are in order. Okay, from the largest to the smallest, from 21 to 6. So this is what the lambdas are, and then let's see. And V, what was V? V itself, this is what it was. So we get this one. This is the matrix which is carrying the eigenvectors. So now that we have this, when we said that the eigenvectors of a specific matrix, they provide the basis of this new domain, but they are at the same time the matrix which allows the transformation from one basis to another. Okay, so we found this V, and this V here we update this one a little, and let's see how this will be changed. So the V, it was this before, but this eigenvector here, it corresponded to the largest eigenvalue of 21. Now that they are ordered, we put the column which corresponds to the largest eigenvalue. We put it first, and this one is put from the first column. It goes to the third column here, because now the lambdas are ordered like this. No, wait a second. Maybe we are running the same thing twice, and it's it's like this. So now this V, it is carrying the eigenvectors, and now this domain in X, and again, what was X? X was this, which represents a specific data set. We project this whole data set into a new axis, or into a new basis, and this is what we get. So this is the Y now, and now we can try to find what is the covariance of Y, and the covariance of Y, it is like this. So here we observe that first of all, we notice that the covariance matrix, it is diagonalized, which means that we do not have a projection. So this value of 0, which we denote here, that means that the projection of the second basis onto the first basis is equal to 0. So we have really identified a new basis where they are like Cartesian coordinate system. They are all orthogonal with respect to each other. Even if we are not on Cartesian coordinate system, the orthogonal coordinate systems, assuming, for example, for the spherical coordinate system, we have AR, A theta, and A phi, where the theta is with respect to the z-axis. They are the direction which shows the increase of the angle theta with the direction which denotes the increase in the radius r. They are all perpendicular to each other, but the only difference between this and the Cartesian coordinate system Because this one, in principle, this means that what is the projection of the x-axis on the y-axis, okay? And this value here, it shows what is the projection of the x-axis on the z-axis. And similarly, this is the projection of the z-axis onto the x-axis. So if this was Cartesian coordinate system, this would be 1, 1, 1, okay? Because the basis that we have written over there on the board is 1, 0, 0, 0, 1, 0, or 0, 0, 1. But here, the coordinates, they are orthogonal, but the weight is different, okay? Because this is the projection of a specific data set onto these orthogonal axes. So apparently, this is what we observed. So if you remember, the Cx was not orthogonal, it was not diagonalized, which means that the data, it is distributed such that the projection of x onto y is 3.8, the projection of x onto z is equal to 4.2, and this x, y, z, we just mean that three major components that which can serve as a basis. So this is where we stopped the last week. Now, this is the example that we're discussing. So we just did the diagonalization using the eigenvectors. In fact, we are saying eigenvectors, but in principle, this is SVD, okay? So we just try to hide the procedure by multiplying the matrix A with its transpose and so on. So Cx, it was not diagonalized. We got the new y, and the Cy, the covariance matrix for the y, new data set. So it will look differently. But one thing that we can check here is to check. So if this is the y, we can find what is the mean of y of the first row. I don't know how we can do this. Wait a second. This is the first column or the first row? The mean, I don't remember. No, this is the column. Okay. How did we find the mean here? We found the mean of the second, okay. Mean y2. Okay, they are not, how, if you compare this with the mean of x, how are these? They should not be equal, of course, because it's a new domain. Okay, but they're, Now I wanted to make an argument, but it's not the case. I think. But wait a second, the x. I'm afraid that comes here x in a little bit. Anyway, I raised the x value, it was here. Anyway, okay, let's skip this. So here we're just saying, in principle, that we are doing the diagonalization by the eigenvalues. And so which means that we are using, but we also looked at the sigmas were equal to the lambdas, the square root of lambda. Okay, so here, let's see. We can look at a different example, which is defined as so if we have, let's do this. So here we have a data set which is x. Now this x so this x, I just want to show this here in order to understand the code that we're going to see after a few minutes. So given this x, this reports only the second column. So if we see here, this 258 is the second column. But if we say from 1 to 2, that means that we are considering x including the columns, the first one and the second one, okay? And then let's have the x again. And here, if we say from 1 to 3, this means that from the matrix x, we're going to consider only the first 3 columns. Now, for much larger data sets, this might be a little more complex. So let's end this section. So what we can do here is that we can generate a 2-dimensional space or a 2-dimensional grid, and we have done this a lot when we used to calculate the Fourier transform of specific data sets. And the way that we did it, if you remember, was that we had kx and ky, and using the mesh grid function, we just prepared a matrix with precise locations in x and y, and on top of that, we can define a function. So here, we just define the x and the y. This is what they are. And there are values for, so apparently x is changing from 0 to 1, t is changing from 0 to 2 in 50 different steps. And we created also the mesh grid. And we can see actually t itself is 25 by 50 and x is also 25 by 50. So we can evaluate all of these. Now we can also define a function f, which is a function of capital X and capital Y. So now this plot that we did, which is changing along the x from 0 to 1, which is one of the x's here, and the other axis was from 0 to 2, this is how the function looks like. Okay, so if we try to rotate it, this is what this is how it is constructed, and then so apparently this f, this is the data set. So we can also check what is the size of f. 25 by 50. So this one in itself, it's a matrix, okay? It's a matrix, and this matrix, we can calculate the decomposition of this matrix, which is in U, S, and V. And let's have a look at S, matrix S. It's hard to see, but let's see 1 to 5, and also 1 to 5. The sigma value, which is this, demonstrating the weight which is on each of the principal axes. So it's here is 47, it's 2, 2.02, 0.4, 0.0106. So similarly, we can go, let's say, 11 to 15, 11 to 15. Let's see what the values are. The sigmas down there, they are 10 to the power minus 9 times all of these values. So here we get 10 to the power minus 9 times 10 to the power minus 3. This is 10 to the power minus 12. This is the epsilon for few computational units or computational machines, which means that these are in the, well, in the decreasing axis, decreasing order. And here we can plot the values of sigmas, and here they are. So here we can add so these sigmas, they go from 47, which is 10 to the power, which is 47 here, then they are a little bit more than 10 to the power 0. Then here we get the values 10 to the power minus 8, 10 to the power minus 10, 10 to the power minus 16, and these are all of the sigmas. Now, what these graphs show, so these values, they denote how the, so this is U, it's representing a new basis, and this is showing the first column, okay, of U. This is representing the second column of U, and this is the third column of U. So these are, this is how the projection of these U can be shown, okay. And this would be also the projections of the V and U. Actually, let's have a look at what U is. As you said, it's a rotational matrix. So if we try to find the determinant of U, determinant of U is equal to -1, which is a rotational matrix. Determinant of V, it's also -1. And if we check what is U, all columns, sorry, all rows first column transpose, if we multiply this one with all the rows, but we multiply with the third column, we get 0, okay? So this is a rotational matrix because all of the columns, they are also orthogonal. So we can do the same, so it's also 0, we can multiply with it can take the dot product of the first column with the second, or the 21st with the 12th. So they are all zeros, which ensures that we are talking about matrices which are rotational ones. And also similarly, we can also find what is the norm of U of each of the columns. It's 1. This is the first column, this is the fourth column, it's 1. So apparently, not apparently, it's a given that rotational matrix, they are orthonormal. And orthonormal, there means that all of the columns are normalized to 1. And they are also orthogonal. All columns are perpendicular with respect to each other. Now, it's also good actually to look at, not good, we can also have a look at the sizes of these matrices, because we have here U S V transpose, we said, right? This is 25 by 25. The sigma is 25 by 50. And then we have here 50 by 50 again. And by the way, apparently, I've made a mistake on the board. I've skipped it, now I remember, because let me see if it's still in there. Yes, this is still here. So this is m by n. So this is m by n. Since this is a rotational matrix, this should be squared. Okay? And this is m by n and n by n. Okay, now this looks better. I mean, this was wrong. Wait a second, yes. Rotation, rotation, but they are rotating on different domains. This is 25 by 25, this will be 50 by 50. And yeah. So this one is a matrix which does not have to be a square one, okay? But the values are located in the diagonal axis. So you find it at sigma 1, 1, sigma 5, 5, sigma 10, 10. This is where they are located. And then what we can do here is that we can try, so let's see, this is the F, right? This is the F, and we can try to do the following. What is F minus U times S times V transpose, okay? Well, this is what we got. So this is a large matrix, but all of the entries in this matrix, these are multiplied by 10 to the power minus 14, okay? Which is, they're almost 0. Which means that to a very good approximation, this data set F, whose graph looks like this, not this, but it's there was this beautiful, colorful, so this is the F. The graph of F is this one. If we do the decomposition, we see that F minus U times S times V transpose, they are almost 0, so they are equal with respect to each other. Now, what we can do, as you can see, this F itself, we can put it right here. Sorry, no. Anyway, F is equal to U times S times V transpose. This is F, but let's do this. Assume that J is from 1 to 3. If J is from 1 to 3, this means that FF initially, this will include U, all the rows, but only the first column. You see, because this is from 1 to 1. Times S, J is still 1, so let's assume that J is equal to 1 still. So this is what this is doing. This is picking up only the first, what's the name? The first column of U. This is including first column of U. This is including only one value for S. So it's including S11, okay? Times the first column of V transpose, okay? So if we have a look at what was the size of U, the size of U, it is 25 by 25, okay? So if it is 25 by 25, that means that for the first column, we are considering only 25 values, okay? Which are located in 25 by 1 times a single sigma, sigma 1, times the V transpose. So this is going to be a single row, which is 25 by 1. Is it correct? Or 1 by 25? Because the transpose, it will be 1 by 25. No, this is 1 by 50. The V, it was 1 by 50. And this sigma 1, in fact, this is 1 by 1. Okay, this is what it is. So here we have 25 by 1 times 1 by 1. This is 25 by 1. So if we multiply 25 by 1 by 1 by 50, we get a matrix A, or in this case, let's consider this F, which is 25 by 50. Okay, so we can reconstruct the whole picture that is shown here in this graph here only by multiplying, by using how many values? Here we have 25 plus 1 plus 15. So this is reconstructing the whole picture, the three-dimensional structure, by using 76 values. Okay, so we can even consider compression in this in here, because instead of using 25 by 50 different values, we are just using 76. Okay, so using singular value decomposition is also one approach or one technique to let me say, to compress the data set. Now, the second trial is to use values, two columns, which would be 1, minus 1, 3, 4, etc., which is going to be 25 by 2. Okay. Then we multiply this one by a matrix which is 2 by 2, which here is going to include 47 something. This was around 4. And then we multiply this here by 2 by 50. Okay, and again, this is 25 by 50. So we're going to have the same size of the matrix, but now this is composed of how many different data points? This is 25 by 2, this is 50, plus 4. In principle, here are 2, because these are zeros, plus 100. So apparently, this is equal to 154 different values. I know that you are seeing my screen, but I believe you can also pin to my camera, at least for now. If you re-see this one later, you cannot see this, because it will not be recorded. But apparently, so this is what we are doing here in this for loop. So we are considering to reproducing this FF as using not the whole U, but using only the first column of U, and here we use only the first column of V. So if we do this one 3 times, going from 1 to 3, as a result, so if we do this, okay, so this is what we obtain. So this is the simplest, the most compressed data set, because this is using only 76 different values. The second one, this is using 154 different values, and this one is using a little more. Now, if you observe here, actually I don't know why I don't see the original plot. The original plot will be in one. Wait a second, so this subplot, so it's a mistake. Oh, okay. Why? Okay. So this is the original function. So this is error-free. These have some errors because we've tried to compress those, and probably in this edge here at the bottom, we see some slight difference. But this difference at the bottom corner down here, where the mouse is, this is minimized when we use some more values. Now, what we can try here is that this j, this is from 1 to 3, so we have 3 values. We can do this one from 4, wait a second, from 4, 5, 6. We go to up to 6. So we can generate them again, evaluate selection. Okay. Oh, okay, no, it's a mistake. So then, if we put this subplot j plus 1, we then just do j plus 1. This will be 2, 4 plus 1, 5, 2 minus 3. Okay. So this is better. But maybe it's best if we so that we make sure okay, so and again we need this. So now these graphs are much closer to each other because here we are assuming that j goes up to 6. When j is 6, this means that we're going to use from the matrix U, we're going to use from the first column to the sixth one. So we are using 6 first column of U, a matrix S which is 6 by 6, and also 6 different columns from the V. And the results, they should look way better. But we can only provide a qualitative evaluation by human perception and not much quantitative evaluation. Okay, for a quantitative evaluation, we can simply do a subtraction of the, so I don't know what FF is, what is the last calculated FF, but we can try to plot, we can say figure 5, we can do surf F minus FF, where F is a precise value or error-free one, minus this. And let's see, okay. So it looks like the difference between the original graph and the FF, which is the last generated value, which corresponds to the first 6 columns of U and the first 6 columns of V, this is what we see. So there is an error, but on the y-axis, we see that there is something like 10 to the power minus 6. Okay, so these we're talking about relatively small values. So the differences are actually this is the amplitude. So we're talking about 2 times 10 to the power minus 6. This is how small these differences can be. And well, we can try from 14 to 16. And then here we have to do, this will be 2. This is 14 plus 1, 15. 15 minus 13, okay. Then we need to do this. Close all. We can do this. Now again, we might use human perception, or we can immediately come here and do the same. So this is what we observe. So if we use more rows, this is for sure it's expected also from you, from all of us, that now we see the difference between the precise value and a very close approximation. We have, it's almost 0 because it's 10 to the power minus 15 times these values. 10 to the power minus 15 is relatively small. We see that there are some errors predominantly at the edges, but it might depend on the function. Okay, so this is how we can try to implement the SVDs. And now, regarding the projects, one of the projects which can be considered for us is doing compression using singular value decomposition. Here, we can do a stop presenting here.